All right, let's continue looking at conic sections. So last time we looked at the circle, and today we're going to look at the ellipse. And hopefully you watched the other video where it showed you that there are lots of interesting applications for conic sections, things like satellites and GPS systems and things like that. So let's talk a little bit about something that was mentioned in the video, how all the conic sections have a point and distance relationship. So we know for a circle that you have a fixed point, the center, and you have a fixed distance, the radius. So the circle is that set of points, which is that distance r from the center. Well, now let's talk about the ellipse and just pretend this is an ellipse, even if it doesn't quite look like it. So imagine that you took your circle and you stretched it out wide, and you took that center and it sort of split into 2 points. Those 2 points are known as the foci. The singular word is focus, and the plural word is foci or foci. It doesn't matter how you say it. And so we have focus 1 and we have focus 2. Just like the circle has the center, now an ellipse also has a center. But the points we want to focus on right now are the foci. So if you found any point on the ellipse, let's call that point P. The distance from point P to one focus plus the distance from point P to the other focus is always the same. So distance from F1 to P plus distance from F2 to P is always a constant for that particular ellipse. So that is the point and distance relationship. And it can be algebraically taken from that idea all the way through a derivation of the equation. We're not going to do that. What we're going to do is kind of do a more casual derivation of the equation. So remember that the equation of a circle that has center 0, 0 and radius r is x squared plus y squared equals r squared. Well, wouldn't you say that I could take that equation and divide both sides by r squared and get x squared over r squared plus y squared over r squared equals 1, and it's still the same circle? I think so. Now, imagine that I changed the numbers that we're dividing x squared and y squared by, and that gave me a stretch in one or both directions. And now I have the equation x squared over a squared plus y squared over b squared equals 1. It's no longer a circle if a is not equal to b. It's an ellipse. And depending on which one is bigger, A or B, you either have a horizontal stretch or you have a vertical stretch. So this ellipse would have its center at 0, 0, but A and B would tell you how far to go to the left and the right. Now let's take this idea even further and generalize more. So remember that you might have a circle with center HK and radius R, and that circle would be, let's get rid of those. Those don't really belong there, do they? How about if we put them here? That circle would be x minus h quantity squared plus y minus k quantity squared equals r squared. Well, in a similar way, couldn't you divide both sides of that by r squared and get x minus h quantity squared over r squared plus y minus k quantity squared over r squared equals 1, and that's still a circle, same circle. We just rewrote the equation. Now, if you took that and you changed the value dividing by the x term or dividing by the y term, you would stretch it one way or the other, horizontally or vertically or both, and this would get you to the equation of the ellipse, which we will write in our notes. Pre-calc, I think you're on notes 53, and Honors Algebra 2, I think you're on notes 58. So here's the equation of an ellipse with center at HK, x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. That's what we would call the standard form equation. Now, different textbooks vary a little bit in some of the details and some of the vocabulary. I'm not actually going to go over all the vocabulary that I normally would. I'm going to massively simplify this lesson and just give you the very, very, very basics. So we're not going to go into detail about the foci and how their values relate to all the other values and all of that. I'm sorry, but we just don't have time. What we're going to do is look at some examples. First of all, let me say that A is going to be the distance from the center to the side. And then B is going to be the distance from the center to the top. Or you could say from the center to the bottom. It's going to be the same. Okay, let's do some examples. Just reminding you that we also have general form, so we just got standard form here. And general form that we learned last time is the same for all the conics, where you don't have parentheses, you just have your x squared term and then your y squared term and then your x term and then your y term and then your constant and then 0. And all of these numbers need to be integers, not fractions, okay? So that's going to be the same general form for an ellipse, but you're going to notice that A and B are going to be different, whereas when it was a circle, they were the same. Okay, let's do an example. So suppose I have this ellipse, x squared over 16 plus y squared over 25 equals 1. We're going to graph it by hand for part A. Okay, so what's the center? What's H and what's K? The center is 0, 0. What's the value of A? That would give us the distance from the center to the side. Well, A squared is 16, so A is 4. What's the value of B? B would give us the distance from the center to the top. Since B squared is 25, B is 5. Now let's go ahead and make a sketch. Okay. So we have the center, and then we are going to go from the center, right 4 and left 4, and we're going to go up from the center 5 and down 5, and then some of you are much more artistic than I am. Let's see if that can look like a halfway decent ellipse. It's halfway decent, maybe even 5/8 of the way decent. I'm impressed. And typically, if we were studying this idea completely, we would label all these points and label the center. We would find the foci, and we would have names for things like major axis and minor axis and vertices and blah, 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 and we're just not going to go there right now. I hope that's okay. But we are going to go to part B, and part B is graph by calculator. So we're going to take our equation and isolate y, just like we did with the circle. So we have our equation, x squared over 16 plus y squared over 25 equals 1. You know what you could do if you don't want to deal with those fractions? You could figure out the common multiple of 16 and 25. I'm thinking that's 400 because we know there are 16 quarters and $4, right? So let's multiply both sides by 400. And we have 25x squared plus 16y squared equals 400. We don't have to do that first, but it's an option if you want to get rid of those fractions. So we're isolating y, so we're going to subtract 25x squared from both sides. And then we're going to divide by 16. And then we're going to square root. And remember what we did with the circle when we used a graphing calculator was we let one function be the positive root and we let the other function be the negative root. So I just grabbed my calculator and I went to y equals and I typed in one of them. I typed in the positive root, and then I decided to show you a shortcut if you want to be lazy. Actually, just we call it being efficient in math, right? Not lazy. So we're going to be typing the opposite of the whole thing. So I pressed my negative button that was under the 3, and then from here I'm going to go variables, y variables, function, y1, and that just says you're going to take the opposite of what you already typed. That way you don't have to type it all again. Okay, for a good window, let's try zoom square. Let's see how it looks. Top half, bottom half. And it should be connected. It's just that your calculator can't do it, but in theory it is connected, so you would connect those. Let's try zoom standard. We're just not seeing it really proportional because remember that the B value 5 is greater than the A value 4, so it's actually supposed to be taller than it is wide. So this particular view is misleading. The zoom square view was better because everything was spread out evenly on the x-axis and the y-axis compared to one another, so you could see that it was slightly taller than it is wide. Okay, and then we're going to do part C, which is change the equation to general form. Okay, so all we need to do is take the equation, which, you know, we already did some of the work right here, almost all of the work. We're just going to finish the work. So we have 25x squared plus 16y squared minus 400 equals 0. There's general form. We've got the x squared term, we've got the y squared term. There is no x term, there is no y term. We've got the constant, we've got equals 0, and there are no fractions. Cool. Okay, let's move on to example number 2. I think we're going to do 3 examples altogether. Oops. There we go. Number 2. So here we have x minus 1 quantity squared over 25 plus y plus 3 quantity squared over 9 equals 1. And we're just going to graph it by hand. So, what's the center? What's h? What's k? H is 1, k is negative 3. The center is 1, negative 3. What's the value of a? Well, a squared is 25, so a is 5. What's the value of b? Well, b squared is 9, so b is 3. This time a is bigger than b, so it's going to be wider than it is tall. So let's go ahead and sketch that. Oh, you know what? I was about to go 5 units from 0, 0, but I have to go 5 units sideways from my center. So I need to plan for that. If the center is 1, negative 3, I need to go 5 units sideways from that. It's kind of a strange way to label, wasn't it? I don't know why I did that. We'll just do it again. Start something new. Okay. Something like that. So let's place the center 1, negative 3. Now let's go 5 units to the right and 5 units to the left. Now let's go from the center 3 units up and 3 units down. And then sketch your ellipse. Also, halfway decent, maybe 3/8 decent that time. It's a little squished. Okay, that takes care of example number 2. Let's do one more. So suppose we know that we have an ellipse, and we know that its x-intercepts are plus or minus square root 15. And we know that its y-intercepts are plus or minus 4. This is like a puzzle. We have clues. You get to be a detective. I guess I'm mixing up my analogies, but you know, you have all these clues and you get to figure it out. What is the ellipse? We're going to write its equation. Maybe you're a detective doing a puzzle. So I'm going to start with a sketch just to figure out what's going on here. Square root 15. Oh, what is that? That is a little less than 4, right? And of course, we go up 4 and down 4 because that one is pretty obvious, plus or minus 4. Okay, so here we have going to an x-intercept of a little less than 4 and another one of a little less, or a little bit to the right of negative 4, and then going up to a y-intercept of 4 and down to a y-intercept of negative 4. Here is our ellipse. Can you tell what the center is? It's pretty clear just by looking at that the center is 0, 0. And so, can you tell what the distance from the center to the side is? That distance is square root 15, and that is A. Can you tell what the distance from the center to the top is? That distance is 4, and that is B. So let's put all those numbers into our equation. Remember, here's the the generalized but called standard form of the equation. We can substitute our center in there, and we're going to square A, and we're going to square B, and there we have the equation. Okay, here is your homework ellipses worksheet. Check answers, ask questions, send pictures.